Hi, good morning. This session is for discussing day three waves answers. Okay, so question number one, we can say it's about the principle of superposition. We have already discussed this. Now, it is very necessary that you write all the definition exactly as shown in the book, as given in the book or as given in the paper, which I had shared with you guys. So coherence or superposition, you need to make sure that you say two waves overlap or meet, and then the resultant displacement is the algebraic sum. That's what. And the coherent sources, we can see that what is meant by coherence. We can say that waves which are having a constant phase difference is known as coherence. Don't make a mistake for these, these questions. So it's a 3 mark. You will get 3 marks if you write exactly like what is being given to you. Now, the next one is about two coherent waves P and Q meet at a point in phase and superpose, where wave P has an amplitude of 1.5. So we can say the amplitude of P is 1.5 centimeter. And yes, so amplitude of P. So the amplitude of AP is equal to 1.5 centimeter, which is given to you. And the intensity of that wave. So if you're talking about wave P, its amplitude is this one. Intensity is equal to I. Its intensity is I. We don't know exact value, but it's given. And then they say that they are meeting with another one wave, and the new intensity is going to be 3I. Calculate the amplitude of the wave, Q. So this is a very simple question, but we get confused sometimes. So whenever we are getting any amplitude or intensity related questions, the only formula that we have got, intensity is proportional to amplitude square, or intensity is equal to K times A square. So this is the only concept behind this question. Okay. Now, if you get any questions where they relate wave A and wave B, or which is they're giving some information about wire A and wire B, and they're asking what happened to the wire B. For example, maybe they will ask you a question, what happened to the resistance of wire B? So in these kind of questions, it's always better to find the ratio. Now, when you find the ratio, you get the answer easily. Okay, now let's see that the wave A has got an amplitude of 1.5 and intensity is I. So, but I can make a formula for in its intensity. I is equal to K A square. So this is a basic equation. I is equal to K A square, where A is 1.5. So this is the basic intensity equation. Now, this P and Q are now, superposed, and they form the another wave. In that case, I can say that its amplitude is going to be AP plus, amplitude of the wave P plus amplitude of wave Q. So this is its new amplitude. So I can say the resultant intensity, I will write IR is equal to K AP plus AQ all square. This is the resultant one. So I can write it as IR is equal to K times AP is 1.5 plus, let's take it as X all square. Now what you need to do is IR by I. The final intensity divided by intensity I. So this is, I can say that the resultant intensity is 3I. So which is 3I by I equals resultant intensity relationship is K times 1.5 plus X all square divided by the old one is K times 1.5 all square. So let's see, I can say that I and I get cancelled, K and K gets cancelled. So I can write this is 3 equals 1.5 plus X all square divided by 1.5 all square. From this one, you can solve this one, but you can use even the shift solve method given in your calculator, or else simply solving this one. Since both of them, they are square over here, I just want to get rid of it. So I will take root of. So root of this one means this root, this root means it will take away all the squares. So root 3 equals 1.5 plus amplitude of the other one divided by 1.5. So now I can say, I'm just writing here, root 3 multiplied by 1.5 equals 1.5 plus x. So x equals root 3 multiplied by 1.5 minus 1.5, which is equal to, just a second, root of 3 multiplied by 1.5 minus 1.5. I get it as, just a second. So this is going to be equal to 1.1 centimeter. So the amplitude of this one is 1.1 centimeter. Okay, that's correct. Next one, the apparatus shown on in figure 5.1 is used to produce interference patterns on the screen. Laser light of 680 nanometer is used. A is the distance between the slits. D is the distance between the slit and the screen. Light of wavelength 680 nanometer is incident on the double slit. The slit separation is A. The separation between the adjacent fringes is X. So fringe width is X. Fringes are viewed on the screen at a distance D away from the slit. The distance D is varied from 2 meters to 3.5 meter. The variation of D with X is given. So determine this slit separation. So this is a double slit experiment and we have got only one formula, lambda is equal to AX divided by D. And they are asking us to find out A. So we need to A. And lambda, we can say that lambda is equal to 680 nanometers. So it is 680 times 10 to the power minus 9. So that is given. And then the problem is they haven't given, the distance, they haven't given the values of X and D. Instead, they have given a graph. From this graph, I can understand the slope of this graph is what? The slope of this graph is equal to X over D. So I can write lambda is equal to A times slope of this graph. Okay, X over D is the slope of the graph. So let's first find the slope or gradient of the graph. For that, I take this point and I take this point. So this point is 2, X value is 2, Y value is 4. This point is X value is 3 and Y value is 6. So slope is Y2, 6 minus 4 divided by 6 minus 4, and this Y is in millimeter. So 6 minus 4 times 10 to the power minus 3. And X is 3 minus 2. 3 minus 2, which is in meter. So you don't have to do anything. So slope of this graph is equal to 2 times 10 to the power minus 3 divided by 1. So which is 2 times 10 to the power minus 3. As they are asking for slit separation A, I'm going to write lambda. So lambda is equal to A times 2 times 10 to the power minus 3, which is the slope. So A equals lambda divided by 2 times 10 to the power minus 3, which is 680 times 10 to the power minus 9 divided by 2 times 10 to the power minus 3. So 680 times 10 to the power minus 9 divided by 2 times 10 to the power minus 3. So divided by 2 times 10 to the power minus 3. You would get the answer as 3.4 times 10 to the power minus 4. So the answer here is 3.4 times 10 to the power minus 4. That's correct. Now the laser is now replaced by another laser that emits light of a shorter wavelength. We can say that it is going to be a shorter wavelength. On 5.2, sketch a possible line to show the variation. Okay. So it's a shorter wavelength. We can say our idea is lambda is equal to A into slope. Okay. So if lambda is short, or in the new case, if lambda is less, then I can say the slope should also be less. The value of the slope should also be less. So definitely we can say that it should be a lesser slope. So we can start from anywhere over here and it should be always. So I can say that it should be a lesser slope. No, it should not be a So I can say that I may draw something like this, and I will make sure that the slope of this one is less than this. Its slope, I can say that it starts from 4 and it ends up at 6.4, 6.8. It ends up at 7. So 4 to 7, 3 differences here. So I draw it in this, it starts from 2, then I will end up at 2 to 4 itself. Okay, so to be on the safer side, what I will do is its slope should be less. So if I start with 2, I will end up with 4, so that I can make sure this is a lesser slope. So like this. Okay, so how do we understand this one? They say that lambda is less. If the lambda is less, then we can say that lambda is equal to a into slope. So as a remains the same, lambda is less, slope should also be less. That's why it is. Okay, now next one, question number 2. A loudspeaker oscillates with a frequency f to produce sound waves of wavelength lambda. The loudspeaker makes n oscillations in time t. So n oscillations. State expressions in terms of some or all the symbols frequency, lambda, and n for the distance moved by a wavefront in time t. So we can say if it moves, if it produces n oscillation in times, it produces n lambda. So the wave, when one wave is produced, the distance traveled by the wave is equal to lambda. So says there are n waves produced, so the distance traveled is n times lambda. Okay, n lambda. And next one, what is the time? The second one is just to find out the time. So we can say that time is equal to total number of oscillations divided by frequency. That will give you the time. So because total number of oscillation, frequency is the number of oscillation per second. So if 100 oscillations are done and 10 is the frequency, then 100 divided by 10. So it will take 10 seconds, or 100 oscillations are done. And if the frequency is 20, then we can say the time elapsed will be 100 divided by 20, which is equal to 5. Use your answers in one to deduce an equation regarding the speed of a sound wave using F1. So we know that speed is equal to distance over time. And we can say that here the distance traveled one is n lambda, and the time is n over f. N and n get cancelled, f goes up, so the speed v is equal to lambda f lambda. The wave of a sound wave is displayed on the screen of a cathode ray oscilloscope. The time base, you can see the time base is equal to 0.2 milliseconds. Determine the frequency of the sound. Okay, so this is the wave. If I start this wave, it starts from here and it ends up. This is a complete wave. So this is time period. So 1, 2, 3, 4. Four columns is equal to t, and one column is what? 0.20 milliseconds. So 4 into 0.20 times 10 to the power minus 3 is the time period. So basically it is 4 times 0.20 times 10 to the power minus 3. I can say it is 8 times 10 to the power minus 4. So the time period of a wave is 8 times 10 to the power minus 4. And we can see that the frequency and time period are related by the equation f is equal to 1 over t. So 1 divided by 8 times 10 to the power minus 4. So 1 divided by answer, you get 1250. So the frequency is equal to 1250. Just a second, let me check the answer. That's correct. Next one. Two sources S1 and S2 of sound waves are positioned as shown in figure. So two sources. The sources emit coherent sound waves of wavelength 0.85 lambda. So I can say lambda is equal to 0.85. That is the wavelength. A sound detector is moved along parallel to the line S1, S2 along from a point X to point Y. Alternate positions of maximum loudness L and minimum loudness Q are detected. The distance S1x is equal to S2x. So S1x, so if I, okay, this is S1x, and this is also going to be 7.40. 7.4. And then explain what is meant by coherent sources, which I'm not going to discuss. State the phase difference between two waves arriving at the position of minimum loudness that is close to that is closest to the point X. So state the phase difference between two waves arriving at the position of minimum loudness. So what is the phase difference between minimum loudness? If you talk about the phase difference between minimum loudness, the phase difference between two waves arriving at a position of minimum loudness. So minimum loudness, we can say that destructive interference should be formed for getting a minimum loudness. So the phase difference between both of them should be 180 degree. Determine the distance S1y. That's the next one. S1x is equal to 7.40. When I was doing it for the first time, I was also getting a little bit confused. I used different methods to get it. But this is very simple. So S1y is this red line distance. And so here the waves are coming from, like I can say that the waves, the red waves, you can think the red waves going over here, and the wave from S2 is also going over here, and there will be a like loud sound. So we can say that it will be constructive interference. So here, what is the path difference between this one? I can see that's one loudness to the next loudness is lambda. This now this lambda. So basically the path difference between these two waves is going to be 2 lambda. So I can say the path difference between, this path difference between these two waves reaching over here, it is going to be 2 lambda. So I can write S1y minus S2y should be equal to 2 lambda. S1y is, we need to find out, S1y minus S2y is 7.40 equals 2 times 0.85. So S1y equals 2 times 0.85 is 2 times 0.85 is 1.7. So 7.40 plus 1.7. So if you add this one, 8.1, 9.1. So S1y is equal to 9.1. So here we use the idea that the wave coming from S1 to this point Y and wave coming from S2 to point Y, they are constructively interfering. They are constructively interfering means we can say that they are having a path difference of n lambda. So if you look over here, the path difference over here to here, it is going to be 1 lambda. If it is this 1 lambda, 2 lambda. So the path difference is 2 lambda, and I use this idea. Now, for a progressive water wave, what is meant by displacement and amplitude? I'm not going to discuss that. Two coherent waves X and Y meet at a point and superpose. This phase difference between the waves at the point is 180 degree. The wave S has got an amplitude of intensity I, and wave Y has got an amplitude of I discussed. I will discuss this also. So let's see that this is X. Wave X, when we talk about wave X, okay, X has got an amplitude. So amplitude of X equal to 1.2 centimeter, and its intensity is equal to I. So I can write K times 1.2 all square equals I. And amplitude of Y, the wave Y has got an amplitude of 3.6. I can write, so AY is equal to 3.6 and 3.6. Calculate in terms of I the resultant intensity of the meeting points. So they say both of them are meeting at any point and the phase difference over there is 180 degrees. So I can easily say that there is destructive interference. So the net amplitude will be equal to 3.6 minus 1.2. So which is 2.4. 2.4, yes. 2.4 centimeter. 2.4 centimeter is the net amplitude. Okay. So now you need to calculate what is the intensity. You can say the intensity I is equal to K times 2.4. The resultant intensity IR is equal to K times 2.4 all square. And we can say that intensity of this one is I. So I is equal to K times 1.2 all square. Since you know that this is, we need to express it in terms of I'm going to divide both IR by I. So this is K and K get cancelled. So IR equals 2.4 all square divided by 1.2 all square into I. So resultant one is 2.4 square divided by 1.2 square. It's going to be 4. So resultant intensity is equal to 4 times the intensity given. So same thing. Monochromatic light is incident on a diffraction grating. Describe the diffraction of the light waves as they pass through the grating. So there is nothing to write in this question. This is monochromatic means you need to tell that single frequency or single wavelength incident on diffraction. So when the light is passing through the slit, it gets spread out. That is the answer for this one. So as it spread out, we can say that as the wave is passing through the small opening of the grating, it gets spread out. That's the answer. I will share the answer scheme also. A parallel beam of light consists of two wavelengths, 540 and 330 nanometer. The light is incident normally on a diffraction grating. The third order diffraction maxima are produced for each of this wave. No higher orders are produced for either wavelength. Determine the smallest possible spacing. Okay, we need to find out the smallest possible. So smallest possible out of this 540 and 630. So our idea is we know d sine theta is equal to n lambda. So d is equal to n lambda divided by sine theta. So value will be smaller. No, d value will be smaller for, because we can say that both of them n for both of them is 3. And theta should be 90 degree. We can say that because they are talking about the maximum. Third order diffraction maxima are produced. So we can see till third order means the maximum angle. 90 degrees the maximum angle. So if it is fourth one, then it goes beyond 90 degrees. So theta. So if you look at this equation, d is equal to n sine theta. We can say that n is 3, sine theta is also same for both of them. So if you want to get a smaller one, the lambda has to be smaller. Lambda has to be smaller among this. The smaller lambda among this one is 540. So let's see that d is equal to 3 times 540 divided by sine 90. So that is 540 nanometers. So again, you will have to put 10 to the power minus 9. 3 times 540 times 10 to the power minus 9. Yes, so 1.62 times 10 to the power minus 6. So 1.62 times 10 to the power minus 6. Just a second, I need to check the answer. Okay, in this one, there is a small mistake. Here, determine the smallest possible line spacing. Smallest possible line spacing or smallest possible line spacing. So the distance between the lines should be really, really small. If the distance between the lines should be really, really small, then D is the width of a slit. Width of a slit means we can say that when the distance between the slits are really, really small, D will be more, right? So in that case, instead of using 540, it should be 630 here. Okay, so that's the only difference. So when you put this one over here, D equals 3 times 630 times 10 to the power minus 9 divided by sine 90. I think it is 1.9 something. Let's see that 3 times 360 times 10 to the power minus 9. Oh, sorry, 3 times. Okay. 3 times 360 times 10 to the power minus 9, which is going to be, just a second, which is going to be, so 3 times 630 times 10 to the power minus 9. So you get it is 1.89 into 10 to the power minus 6. So this is the same idea. 540 nanometer and 630 nanometers are the two waves. And both of them are making third diffraction, third order diffraction. So 90 angle is equal to 90 and n is equal to 3. And determine the smallest possible line spacing. So smallest possible line spacing എന്ന് പറയുമ്പോഴത്തേനും we need to understand that the width of the slit is going to be, smallest possible line spacing എന്ന് പറയുമ്പോൾ there should be maximum number of slits. Now, number of slits are വരേണ്ടത്. So, അതുകൊണ്ടാണ് ഇവിടെ 630 എടുത്തത്. Okay. If you have got any further doubts, we will discuss. The beam of light in C2 is replaced by a beam of blue light incident on the same diffraction grating. State and explain whether the third order diffraction maximum is produced for this blue light. So when you talk about this blue light, we can say that the blue light frequency, the wavelength of waves is basically from 420 nanometer to 720 nanometers. So if you say, I can say that this is from wave or. So now this is about 630 and the blue light, its wavelength, its frequency will be even less. So this one, we can say that d sine theta is equal to n lambda. So we can say if the wavelength has gone down, then we can say that the n value will be greater. So there is third order maximum will be formed. So d is same and sine minus 90 is same. Then we can say that lambda blue is less. So now this product n into blue should be greater. So the n value should be, that should be a third order or more than third order should be formed over there. Now the last question. A vertical tube of wavelength 0.6 millimeters is open at both ends as shown in the figure. The incident sinusoidal waves of single frequency travels up the tube. A stationary wave is then formed in the air column in the tube with antinodes A at both ends and nodes at the midpoint. Explain how a stationary wave is formed in the incident sound. So we could say that a stationary wave formed over here means the wave passing through the tube reflects and come back. So the reflected wave and the ongoing wave overlap. So you need to tell them that the wave get reflected from the top of the tube and then it interfere with the ongoing wave. So two waves moving in the opposite direction superpose and it forms. Sketch a graph to show the variation of the amplitude of the stationary wave with height h above the bottom of the tube. So we can say that amplitude over here, the amplitude is antinode. So it is a maximum amplitude. Here the amplitude should be 0. Here the amplitude should be maximum again. So if you are drawing something like this or here, this in the middle is 0.3. It's 0. So 0.3. You can start with anything. Amplitude is maximum. Then 0.30, it should be 0. Amplitude should be 0 at 0.30. So 0.2. So this is 0.30. At 0.30, it should become 0. So amplitude, maybe I can say that it goes like this, straight line. It should be a straight line. If I start from here, straight line, then it becomes 0. From here it goes again. It should be same over here. That is how it should be drawn. That's it. For a stationary wave state, the direction of oscillation of a air particle above at a height of 0.5 meters above the bottom of the tube. Okay. There are mostly students make a mistake. Hello, I got stuck. Hello, yes. Okay, so this is, as we draw, we think, we feel like if it is like this, we draw the stationary waves in different patterns, but here the waves are going in this direction. So the vibration is basically happening this way. The vibration is waves again. Here it's not, there is no vibration happens, but here I can say that the vibration of the particles are maximum. Here also the maximum one. But they are asking about 0.15 or something. So I can say the vibration will be this way. The vibration is, now students tend to draw that vibration is this way. No, that is wrong because the particles are going up. So the vibration will be along the line. This will be this way because air particles vibrate forward and backward. So sound particles over here will vibrate forward and back. Sound particle is not going to the sideways over here. We get confused because we draw the wave like this, right? Now, so we think that the vibration is taking place in this way. This is taking place in this way if there is a string, and the string, this vibration will be going in this way. But this is sound waves. Sound waves are longitudinal waves, so its vibration will be this way. Okay, I think you need to note that. Just a second, let me confirm it. So vertical, they say that the line has got, okay, the vertical along the length of the tube, along the axis of the tube. So it should be that way itself. Now the next one is the frequency of the sound waves is, sorry, the speed of the sound wave is 340 meter, calculate the frequency. So they say that it's on the pipe. Here it is, okay, so this is antinode over here. Then I can say that node over here. And so this is the pipe, right? In this pipe, this is the waves formed. So we can say that 0.6 length is equal to, if I say this, as I do, like this one, it is from one antinode to the next antinode. This is lambda by 4. This is 2 lambda by 4. So 2 lambda by 4 is equal to 0.6. So lambda is equal to 0.6. This is times 2. So lambda is equal to 1.2. Then we can see, so V is equal to F lambda, or F is equal to 340 divided by 1.2. So you got the frequency, 340 divided by 1.2. And that is going to be 283. 283. That is also correct, I guess. 200, yes. The frequency of the sound wave was gradually increased. Determine the frequency of the wave when the stationary wave is next formed. So let's see that. If we have got a stationary wave this way and this way, I can say this antinode formed. Now the next one is this antinode. So this is from here to, so lambda by 4, 1 lambda by 4, 2 lambda by 4, 3 lambda by 4, 4 lambda by 4. 4 lambda by 4 is equal to length of the pipe, 0.6. So lambda is equal to 0.6. So frequency is equal to speed divided by wavelength, which is 340 divided by 0.6. 340 divided by 0.6, you get it, it's 567 hertz. Done. Okay, that's what all for this. If you have a particular doubt for me, you may have doubt for this question, which we will discuss in the class. No, not discussion. This question. If you have got further doubts, we will discuss in the next class. Thank you so much. So make sure you go through this one, understand, then do day 4's worksheet. Bye.